Hi, I'm Rhett Jesse, and today we're going to talk about the Metrix digital proximity system. Specifically, we're going to talk about how we eliminate crosstalk. Crosstalk occurs when you have two probes that are close together. And because they're at the same frequency, they talk to each other, and it causes a problem. Typically, probes are 2 inches or 50 millimeters apart where you don't have that problem. But anytime you have two probes close together radially, or maybe one radial, one axial, you can have this problem. So what we're going to show is how we get rid of it during this demonstration. And to do that, we're going to use the Metrix 2034 digital proximity system. Well, this is kind of special in that it has 4 pins. Right? 2 pins go to loop power, and that's what powers the device. And then the other 2 pins go to signal and what I have marked here as ground. There's signal and common when it goes to your monitoring system. So signal and common. That goes to your monitoring system. These 2 go to your loop power. So that's how I've got this system set up. And what I have is I have the raw signals from those signal and common going to the set point monitoring system. On the set point rack, we have the radial vibration probes X and Y, channels 1 and 2 going into slot 3, channels 1 and 2. And then we have the thrust transducer going into slot 4, channel 1, and the phase triggers on channel 4 of slot number 4. So we've got all the signals, raw signals, going into the set point system, and that's going to gather our data so we can look at this noise problem. All right. The transducers are energized, but the rotor is not running. And so what we're going to look at is look at the software and see this noise problem. So when I look at the set point software, we're getting data live right now. And you can see on the Y transducer, which is vibration channel 1, we have 0.92 mils peak to peak of vibration. And then on channel 2, we have 2.04 mils peak to peak. And the rotor's not even running. And you can tell right away by looking at that signal that it's a noisy signal. What I'm going to do is I'm going to disconnect the Y transducer, radial vibration 1, and we should see radial vibration 2 go to 0 because it's really not vibrating. I have this sort of disconnected because what I've done is I've removed the DIN rail mounting these 3 screws so I can get to the USB port so I could change it, the frequency. I can use crosstalk elimination. So that's what I've done right now for my setup. That's why this is a little bit askew. So what I've got is I'm going to disconnect this transducer, and what we'll see is that signal will go away. And we'll see that. We'll update here in just a second. Okay, so you can see that radial vibration 1 went to absolutely 0. There's nothing on it. And that's because it's totally disconnected. And then you can see on channel 2, we've got a little bit of background noise, 0.2 mils peak to peak. So that's not bad. So what we have is a little ambient noise, and that's really not bad for a transmitter. Our driver does a little bit better than that, but the transmitter 0.2, that's actually pretty good. Now, I'm going to go ahead and connect it back, and we're going to bring our noise back. And so that lets you know that we really do have a noise problem. And if you think you have a noise problem at your plant, as long as you've bypassed the channels, you can do the same thing. You disconnect the channel, and if your noise problem goes away, you can pretty much know that they're talking to each other. So now what are we going to do about it? Well, I'm connected to this system, and I can change its frequency. But before I do, let me go ahead and start up this rotor and let me show you what a bad signal looks like when it's vibrating. All right, now this machine, you can look at it, and I'm asynchronously sampling. What I'll do is I'll put a phase trigger in there and we'll synchronously sample. And when that updates, what you'll see is that instead of having the phase trigger being stable, it will be moving. And the signal itself looks very scratchy. It looks like there's a lot of noise on it, and that's all bad. We want to actually get rid of that. And so this is the problem that noise causes in your signal. So what I'm going to do is I'm going to shut down, and I'm going to switch the frequency of my Y transducer, I'm going to switch it from the X, which is the normal frequency, to a Y, which will basically force where this frequency is different from the other. So we're going to go ahead and do that now. So I'm going to change the frequency of the Y transducer to a Y frequency. We're going to force a separation. And to do that, I start the digital proximity system software. We can see on the software that we're already connected. You can see the serial number 111951, and that's the same serial number that's on this digital proximity unit, 111951. And you can see the rest of the configuration. This is vibration 4-wire. We're looking with MX8030 probes at a 4140 target, 8mm probe type, a 1-meter probe. And that's one thing I did before this setup. Instead of having 5-meter systems that are traditional, I just took out the extension cables, reconfigured everything for a 1-meter system to make the system look a little bit cleaner. Makes it easier for us. So what we'll do now is we'll go to the advanced settings, and we're going to change the frequency of the transmitter to Y. Now you can do the same thing with the driver. So if I had a monitoring system and I had Crosstalk, if you had our MX8030 probes with the MX2034 transmitters or MX2033 drivers, you can eliminate this crosstalk. So it works with either one. So let's go ahead and change it to Y. And we'll say OK. And right as it updates, you'll start to see a change in the screen in the set point system, because it's going to basically sense that we don't have this crosstalk problem anymore because we've shifted the frequency. And you can see how it's updated. We'll go ahead and let it finish updating and make sure the DPS is fully changed. And then after that, we'll go ahead and look at the vibration signal, and that shows you crosstalk elimination. We'll go ahead and minimize this. And you can see now our ambient noise level is down to 0.18 and 0.15. That's very good, excellent for a transmitter. And let's go ahead and start up the machine and see if it behaves any better. Software is updating. All right, I'll go ahead and take off asynchronous sampling, and we'll just look at synchronous sampling. Look what the phase trigger looks like, and now it's a much cleaner signal, much better than it was before. And we've removed all that noise. And so that's the power of being able to eliminate crosstalk, and you do that by shifting the frequency. And we can do that with our system. Let me go ahead and shut down. We'll go ahead and take a look at the ambient noise level one last time. We'll let it finish up. Go ahead and bring up asynchronous and just let's look at what it looks like. You know, with the transmitter time, you're less than 0.2 mils peak to peak. That's really excellent. And really that's where we're at, 0.14, 0.18. That's outstanding. In summary, what we've done is we have two probes that were close together, either XY in a radial manner, or maybe we have an X with a thrust transducer that are close to each other. What we did is we went in and we said, let's change the frequency of one of these transducers, so that way they no longer conflict. Now we did that with our 4-pin transmitter that we have here, and we can also do that with our driver. I think you'll find it very useful at your plant. Thank you very much.